Hi, this is Sharon Evans. I'm here to talk about the chain rule, which is a method for finding the derivative of a function that is a little more complicated than the functions we've looked at so far. An example of this might be if h of x equals the function 3x plus 5 quantity cubed. To take the derivative of h of x using the methods we've studied so far, I'd have to expand this. So I would have to multiply 3x plus 5 by 3x plus 5 by another factor of 3x plus 5. Something I really don't want to do. Instead, I'm going to look at h of x as the composition of two functions. So if I look at h of x as the composition of the function f of x, which is x cubed, and g of x, which is 3x plus 5, it's much easier to take the derivative. I see f of x in this case as my outside function, and I see g of x as my inside function. And when I compose them with f composed with g of x, meaning I put g of x inside f of x, I get h of x. So remember, the definition of a composition means, in this case, I start with f, which is x cubed, and I put g of x inside, so 3x plus 5 on the inside of f. The chain rule will allow me to take the derivative of h of x, so h prime of x, using f of x and g of x. And we'll define h prime as the derivative of f, so f prime evaluated at g of x multiplied by g prime of x. So f prime evaluated at g of x, so if I just off to the side say, all right, well, f prime will be the derivative of x cubed. So that's just 3 times x squared. F prime evaluated at g of x means substitute g of x for x in the f prime rule. So I'll make this 3 times not x squared, but 3x plus 5 squared. So here I've plugged g of x in, I've put g of x on the inside of f prime of x. I've plugged g of x into f prime. So f prime evaluated at g of x is simply 3 multiplied by the quantity 3x plus 5 squared. Finish taking the derivative, I simply multiply this by g prime. So g prime is just 3 because I take the derivative of 3x, which is 3. The derivative of my constant 5 is 0. So I'm going to multiply my expression here to complete my derivative by g prime, which is 3. So h prime, and I'll multiply 3 times 3 here, is simply 3 times 3 is 9 times the quantity 3x plus 5 squared. This is certainly easier than expanding 3x plus 5 quantity cubed and then taking the derivative of each piece of that. Let's take a look at another example. This time let's let h of x be e to the power of 2x plus 1. So I'll define my outside function f of x as e to the power of x, and my inside function g of x as 2x plus 1. So I see that h of x in this case is f evaluated at g of x. So remember, f is e to the power of x. However, I will plug g in for x, so this exponent becomes 2x plus 1. So h prime of x will be f prime evaluated at g of x multiplied by g prime of x. So I can, off to the side, I know that the derivative of e to the x is just e to the x. F prime evaluated at g of x is e to the, not x, but 2x plus 1. So I'm substituting g here for x. So my derivative of h of x, or h prime of x, will be e to the power of 2x plus 1 multiplied by g prime of x. So I'm going to multiply f prime evaluated at g of x by g prime of x. And I see that g of x is 2x plus 1, so g prime is simply 2. So I'll multiply by 2. So I see that h prime of x is simply 2 multiplied by e to the power of 2x plus 1.